right, so good afternoon, everybody, and welcome to another exciting broadcast with us here at Exploring by the Seat of Your Pants. I know we've got a big new audience today. Some of our classes joining us for the very first time ever, in which case, welcome to the broadcast. We are all about bringing conservation, adventure, and science into classrooms around the world. Now, everything we do goes live to our YouTube channel and stays there forever. So if you want to catch this later, if you want to watch it in 3 weeks or 3 years, or watch like 3,000 other broadcasts, they're all right there for you to check out. Lots of opportunities to keep the learning and excitement going. We are also going to have a Kahoot today. So I know a lot of you are new to this too. 4 quick question quiz, have a little fun, test your understanding, have a good time. You can pull this up in a separate tab on the top of your screen, 703-1802 kahoot.it. I'll be sharing that a couple more times in the chat as well, so make sure you don't miss it if you want to play along. Now, October is classically our epic space exploration month. We just put out our newsletter this morning with, I think, 15 broadcasts with amazing NASA personnel and more. I really encourage you to check that out, sign up. We got some great stuff, including with 2 astronauts, but we wanted to start a little bit early. October's too far away. It's like, it's on the weekend. It's crazy. It's way too in the far future. So we're bringing on Mike Grudic today. He is a NASA fellow. He's at the Carnegie Observatories in Pasadena, California, coming home now. He's actually just like down the street from me, which is very exciting. And today he is going to talk about star formation. So we are in a solar system. We have seen these amazing James Webb Space Telescope pictures. We just announced our contest around that. The thing that underpins our universe are stars. And today, his work at the STARFORGE Project, which is the coolest project name of all time. He's going to explain a little bit about the amazing work that he does to understand how stars form and how the universe around us forms. So I'm pretty excited about that. I hope you guys are too. So excited to dive in and get underway. And without further ado, joining from the best virtual background of all time, Mike Grudic. Welcome in, man. So nice to see you today.
Great to be here.
Well, I know you've got a lot to share with us. We got our Kahoot. We got lots to cover. So if you want to dive right in, I'll bring up your presentation full screen, and we are golden, man.
Perfect. Let's do it. All right. Hey, everyone. I'm Mike. And today I want to talk to you about the universe's secret recipe for stars. So why secret recipe? Well, it turns out that if you want to make a star, there's all sorts of different ingredients that have to come together in just the right way. And why is it a secret recipe? Well, it turns out that it's actually kind of a complicated story. It's so complicated that the origin of stars is not a settled science. If it were a settled science, then I wouldn't have a job. But well, as it happens, my job is to figure out how stars form. So we'll be talking about all these different ingredients that have to come together to make that work. All right, so let's get into it. So just to get situated, first of all, here's Earth. This is where we live. It's our home. And we know, of course, that the Earth's home is in orbit of the sun. And in fact, the Earth-Sun system is part of the larger solar system that has all of the different planets, asteroids, things of that sort. But of course, our solar system is actually only one of many, many other solar systems orbiting around other stars in our galaxy. So here's a look at where we think our sun is in our galaxy. And if we zoom out, we see that there is an absolutely enormous galaxy, tens of thousands of light years across. And this galaxy contains billions and billions of stars that are just like our sun. But what's more is that if we zoom out even more, the Milky Way is just in the center here, and we see that there are many, many other galaxies. There are billions and billions of galaxies in our universe. And the farther we look, the more galaxies we find. So really one of the key things for astrophysics is just figuring out how did it all get here. That's what we want to do. Now, we have some basic idea of how it all began. The universe began with a big bang, so an explosion from an extremely dense initial hot state from which formed the galaxies and stars and planets and everything that we know. And in fact, the way that the galaxies formed is even reasonably well understood. So starting from the Big Bang at the beginning of time, the universe expanded. Then we had a sort of dark age where there are no galaxies around until eventually the universe lit up about 400 million years into the history of the universe, and the first galaxies formed. And ever since then, galaxies and stars have been forming continuously until today, about 14 billion years into the history of the universe. And we can even simulate the way that galaxies formed over cosmic time, over billions and billions of years. This is a movie from a computer simulation of galaxy formation, where every little blob you see in this movie is an individual galaxy in the simulation. And the way that it works is dark matter clumps up into these blobs that are called halos. And these blobs have lots of gravity, and that gravity pulls gas in. So the gas falls into the dark matter halos, and that gas somehow, once it gets into the dark matter halo, it turns into stars that make up galaxies. And that's essentially how galaxy formation works. Now, this is all a very nice, pretty picture, but there's actually one problem here, which is that, of course, galaxies are made of stars. They're made of billions and billions of stars, but we actually don't fully understand the way that the stars form in any sort of detail. In this sort of simulation, they just sort of have to put in the stars by hand. So it's not self-consistent. So what we got to do here to figure out how star formation works is astrophysics. The essence of astrophysics is as follows. So you point your telescope at something that you want to understand better, say some newborn stars that are forming in a cloud somewhere. So, light from those stars comes into your telescope, and that allows you to collect data. So the data can take many forms. It can take the form of images, or it can take the form of spectra. Now, what are spectra? Well, spectra are when we take the light from the telescope and we break it up into all of the different colors of the spectrum. And based on all of the little bumps and divots in that spectrum, we can gain some sense of what's going on in the thing that's generating that light. So we send those data to the people doing theory and modeling, and essentially what they try to do is interpret what is going on in terms of the known laws of physics. So, of course, our universe obeys a set of universal laws that work everywhere, essentially. They work the same way everywhere. So everything we see around us is following the same set of laws. So if we can figure out how the stuff we see emerges from the way that those laws work, using math and simulations and modeling, then we can learn something about those objects. And of course, if you do that, then you can make predictions. So you can, for example, tell your observer buddy where he should point his telescope next to see something cool. And what will he see? And how do we distinguish between sort of different scenarios based on what he will see? So it all works in a sort of cycle in this sort of way where we have this kind of cooperation between observation or experiment and theory or modeling. And in this way, we can kind of figure out how the universe works. It's great. So, okay, back to star formation. So where do stars form? Well, they actually form in the spiral arms of galaxies. And these spiral arms contain extremely cold gas. It's mostly hydrogen and helium, the two lightest elements. And this gas is unbelievably cold, colder than anything we would ever run into on Earth. So on the Kelvin scale, it's about 10 Kelvin. In Fahrenheit, that's minus 441 degrees Fahrenheit or minus 263 degrees Celsius, depending on if you're in the US or Canada. So these are incredibly cold clouds, and these clouds also contain lots of dust. So here's a picture of the light that's being emitted from the dust in these clouds. And essentially, as stars shine on the dust grains light up. And we're able to pick this up in the telescope. This is a brand new image taken by the James Webb Space Telescope. So if we zoom in on this a bit, we see that the star formation is happening in these sort of stellar nurseries. And these stellar nurseries have newborn stars. And next to the newborn stars, we see this very, very cold gas. And this gas seems to be collapsing under gravity. Now, gravity is the first ingredient in the recipe for star formation. So let's talk about that a bit. So, of course, the way we're familiar with how gravity works on Earth is, for example, it can make an apple fall from a tree, right? It's an everyday thing. We don't think much of it. But one guy in particular did actually spend a lot of time thinking about how exactly this works. So Sir Isaac Newton realized that Apples fall from trees because the Earth is exerting a gravitational force on the apple. And moreover, because every action has an equal and opposite reaction, the Earth is pulling on the apple, but also the apple is pulling a little bit on the Earth. So Isaac Newton was able to sort of generalize what we see in everyday experience on Earth to what is going on in the solar system. He realized that if every body in the solar system pulls on every other body in a certain way, then you can explain the way that all of the objects in the solar system orbit around the sun. So this was a groundbreaking idea at the time. It really is fundamental to the entire endeavor of astrophysics, which is that the same law of gravity that works on Earth works everywhere. So this works for gravity, and it also works for all of the other different forces of nature. And that's what makes astrophysics possible, because of course, if we became familiar with one set of laws that worked on Earth, but it turned out that things very, very far away were doing something completely different, then we'd have no way of interpreting what they were doing. But this seems to be working extremely well so far. So what gravity ends up doing in astrophysical systems like stars and galaxies and star clusters is it pulls everything together. Every object in the universe is pulling on every other object in the universe all at once. And that tends to make matter want to collapse. It makes it want to clump up, and it makes things want to sort of orbit around each other. So gravity is the first ingredient, but of course, we also have to take into account what the gas is doing. So when we look at the way that the gas actually moves around in these star-forming clouds, we see that it is very turbulent. So turbulence is a sort of chaotic, random sort of gas motion that produces very complex structures. So this is a movie of a simulation of just a box of gas that has a stirring force applied to it, a very simple stirring force. But from this very simple stirring pattern arises all of this sort of chaotic motion that just sort of arises naturally from the way that gas likes to move around. So you can see that some very dense clumps and filaments and structures are forming in this turbulent medium. And those dense objects are sort of the seeds that will go on to become self-gravitating and collapse into stars. Also active in stellar nurseries are magnetic fields. So it turns out that the entire universe is permeated by magnetic field lines. So on Earth, we are most familiar with magnetic field lines between just the poles of a magnet. But in fact, there's a little bit of magnetic field everywhere. And as it turns out, magnetic fields can help to resist the collapse of gas clouds against the force of gravity. So gravity makes things want to collapse, but the magnetic field lines, they actually don't want to be scrunched up. So they're going to push back against gravity, and you want to account for that when you're figuring out how star formation works. Now, I've been talking a lot about physics, but there's also a lot of chemistry involved in star formation. So again, consider a cloud of gas. It's got some matter in it. It will collapse. And as it gets denser and denser, what's actually going to happen is molecules form. In fact, most of the matter in these star-forming molecular clouds is the hydrogen molecule, which is two hydrogen atoms stuck together. And when these molecules form, they will emit radiation. So they're actually going to carry energy away, and that's actually going to allow these clouds to keep cool. And if that's important for star formation to be able to happen, because if the clouds cannot cool, then they're eventually going to stop collapsing. So chemistry is very, very important for determining why these clouds are so cold. And lastly, the last remaining ingredient is feedback. So newborn stars influence the gas around them as they are forming. And feedback comes in many different flavors. The first is what are called protostellar jets. So this is an image of a stellar nursery taken with the Hubble Space Telescope. And what you can see is that there are all of these sort of jets shooting in opposite directions. And in fact, these jets are moving at extremely high velocities, hundreds of kilometers per second. So far, far faster than anything we'd ever experience on Earth. And this turns out to be a very important process for star formation. So here's a recent image taken with the James Webb Space Telescope, and you can see the jets sort of come out in these two lobes that light up in the infrared light that James Webb is sensitive to, shown in red there. And what's going on there is that you have this blob of gas that is forming a star at the center. And as the star sucks up gas from the clump, some of that gas is going to get launched along the poles of the star in opposite directions. And that helps to actually pull some gas away from the clump so that it can't reach the star. So it actually regulates how much gas a star is able to suck up. The next important stellar feedback mechanism is stellar winds. So all stars have a wind. They have a stream of particles coming off their surface. The sun, in fact, has a wind. But particularly important in star formation are winds from massive stars. So stars more than 10 times as massive as the sun. As it turns out, the winds from these massive stars can move at, again, thousands of kilometers per second. They carry enormous amounts of energy, and they can just blow apart these star-forming clouds. So once you've formed any of these massive stars, then the winds are just going to blow everything apart, and that determines when star formation ends. Quite similarly, massive stars also emit enormous amounts of radiation. Most of the radiation is not visible radiation like comes from the sun, the visible light from the sun, but rather UV radiation, kind of like the stuff you got to put on sunscreen to keep from getting a sunburn. If we were as close to a massive star as we were close to the sun, then stepping outside, you would get a sunburn in about 1 second. That's how much UV radiation these things are emitting. And this UV radiation does two things. One is that it heats up the gas, which makes it want to expand and again blow apart the cloud. And the other thing that it does is push on the gas. So light actually has a certain force. A beam of light will impart momentum to any object that it hits, and it will push it along. So that's another way to blow apart these star-forming clouds. Now, the last form of feedback we need to talk about is supernovae. So all stars die eventually. Massive stars are particularly short-lived as far as stars go. They only live about 3 million years. Now, that might sound like a long time, but remember that our sun has been around for about 4.5 billion years, so more than 1,000 times longer than that. So 3 million years is the blink of an eye as far as a galaxy or a star is concerned. So at the end of their life, these massive stars become unstable and they blow up. And this explosion has an enormous amount of energy, which again can just blow the entire star-forming cloud apart and help to determine when star formation ends. So that's feedback. And we can now actually put all of these different ingredients we've talked about into a supercomputer simulation to kind of study star formation in a virtual laboratory. So the way we do that is we start with a gas cloud, just some initial state. We break it up into many tiny gas parcels, and then we follow the motion of those little bits of gas according to the known laws of physics. And then we follow the conversion of gas into stars, and all of these feedback processes, and the cloud blows apart, and we're left with a star cluster. And we can compare that with observations to see if we're getting the right answer. And if we're not, then we go back to the drawing board and make the model more realistic. So that is the idea of the STARFORGE project. What we do at STARFORGE is we take all of these different ingredients for star formation that we've been talking about, and this is in fact the first simulation that has put all of these together into one simulation. So we're accounting for all of the different things that we might think are important in star formation, and we can simulate star formation sort of realistically in one of these star-forming clouds. So what does this look like? So here's the first simulation that we fired off with all of these different ingredients put together. So we start with just a ball of gas. It's 30 light years in radius, so 60 light years across, which is enormous. Again, many, many times larger than the solar system. And it has about 20,000 suns worth of gas in it. So if this were converted to stars with 100% efficiency, you can make 20,000 suns. But as we'll see, that's not what happens. So if we start the simulation, we have these sort of random turbulent motions in the gas, and these produce these filaments and these clumps and these dense structures. Eventually, some of these structures will become dense enough that gravity takes over, and they collapse and they form a star. And as the stars form, they suck up gas, and you can see these bipolar jets flying away from the stars. And those jets are carrying away mass with them. So it's regulating the way that stars can actually feed on gas from their environment. So that determines how massive the stars can actually get. And more star formation goes on, and you can see that we're kind of assembling into a central star cluster now and forming more and more stars. And these jets are getting more and more powerful. Star formation is ramping up. And eventually, we reach a point where the combined force of feedback, so all of that radiation, all those jets, all those winds, is able to start reversing the collapse of the cloud and opening up a cavity in the center and essentially blowing it apart. And eventually, the first supernova goes off. That's that explosion you just saw right there. And that essentially is the final nail in the coffin for star formation in this cloud. And this entire sequence of events takes place over about 10 million years. So what we're left with is a virtual star cluster, which we can compare with images from the Hubble or James Webb Space Telescope and essentially see, is it realistic? If yes, then great. But usually there's some sort of interesting discrepancy. So we've got to scratch our heads and figure out, what else we need to put into the simulation. And that's how we learn about how stars form at StarForge. So just to summarize what I've talked about today, so stars form in galaxies, and stars are still forming in our galaxy today, and we can observe it with various types of telescopes, and it happens over a time scale of millions of years in these stellar nurseries, like is shown here. And there are lots and lots of different ingredients that you need to get star formation right in a realistic picture. There's gravity, which pulls everything together. There's turbulence, which sets these random motions and the way that the gas clumps up and makes the seeds that form stars. There's magnetic fields, which resist the collapse of gravity. There's chemistry, which is essential for keeping these clouds cool. And there's feedback in the forms of jets, winds, radiation, and supernovae. And you need to put all of these things together in just the right way to get a realistic star cluster. So that's what we've done at StarForge. We've taken all of these ingredients and we've put them into a supercomputer simulation. And now, essentially, we've built a virtual laboratory and we can start understanding how all of these different things work together to form stars. Because, of course, if we want to understand where we came from, then we need to understand where the Earth came from. If we want to understand that, we need to understand where the sun came from. And to understand where the sun came from, you need to understand star formation. So by understanding stars, we are understanding the story of ourselves. And with that, I'll leave it off. Thank you.
Thank you so much, Mike. First of all, I don't know how you get any work done with beautiful imagery like that at all times. I want that as my desktop background at all times, is that whole simulation. That was awesome. I've done many broadcasts for many of our students. A lot of this will be new. Protostellar jets are awesome. I don't think I've ever seen that depicted that way before. The way they're in the simulation is super cool. So again, I've been sharing your website up online. If any of our classes want to check that out, your personal website, I'll make sure they all have that at the end of the broadcast. What we're going to do now is go into a quick Kahoot together, test some understanding, have a little fun. You whipped through that. You were right on time, which never happens. So I like you more already. If you want to come out of screen share so you can see us again, have a bit of a conversation in a minute, that would be great. But for our classes and the ton of you that are already in our Kahoot, there's our game pin up on the bottom. If you're new to Kahoot, I know some of you are new to these broadcasts in general. The faster you answer, the more points you get. Now, you don't win anything, but you do win Mike and I's everlasting respect, which is pretty good. I think it's well worth it. So we're going to dive in with this in a second. 58 of you already in. Awesome. And then we're going to go to all our live classes, YouTubers for questions. Mr. LeVogue, I'm coming to you guys in Florida first. Miss Albert, Miss Bullock's class, welcome in as well on the broadcast. All right, I'm going to get us underway. Mike, if you want to give us hints in the final few seconds of each of these Kahoot questions, you are more than welcome to. And spoil anything for our students. But let's dive in and get underway. That was so much fun. Man. Okay. 3, 2, 1. Question 1. Okay. I put this in. This might sound easy. It's one of the first things we covered in this broadcast, but so many people don't get this right. The closest star to Earth is Betelgeuse, Rigel, the Sun, or P9122b456, which I just invented on the spot mere minutes ago. What do we think? I could have chosen any number of ones. The other ones. Let's see. Okay. Most of you got this right. A few of you picked Rigel. So our sun is a star. It's like it's very counterintuitive, as we hardly ever hear about it talked about as a star. It is a star. It's a good medium-sized star. It's very wholesome. Gives us light and life and everything else. But it is one. So I'm glad most of you got that right. We'll see where that puts our leaderboard. Bright Koala. Now, Mike, these aren't their real names. Just want you to know, just in case you were wondering. Stars are made of. We talked about this at the beginning of the broadcast. Unique star stuff, like their whole own types of materials. Gas made up of all the normal elements. We talked about helium and hydrogen in this broadcast, or we have no idea. Like stars are a complete mystery to all of us. So many of you in the Kahoot today. This is great, especially for like our first space broadcast of the year. So let's see where our answers come in. Good. Okay, I know these sound simple and you guys are like nailing it. 90+% of you are getting these right, and that's awesome. But a lot of people don't know this. If you know this by grade 5, you are so far ahead of the game in terms of understanding the cosmos around you. So kudos to you. Agent Raccoon takes our lead. Leaderboard's all screwed up on that one. That was exciting. All right, true or false? Very big stars die in massive explosions called supernova. Now, Mike, I'm going to let them answer. I think we're going to get a lot of right answers in this one. Is there I've heard, is it 8 times the size of the sun, 10 times the size of the sun goes supernova? Is there do we have an understanding of exactly where that threshold is or what?
Yeah, no, that's good. The cutoff is about 8, actually. Yeah.
Perfect.
Yeah, I have a buddy who blows up stars on computers, and that's what he tries to figure out.
Just a great line out of context. I love it. So yes, it is true. Very big stars. Our sun will not go supernova. Our sun dies in a really interesting, unique way, which can be vaguely scary for kids, but is super cool in its own right. And everyone should look that up when you're done this broadcast. All right, Agent Raccoon has our lead by 11. It's like the tiniest margin going to the final question ever. How many stars are there in the universe? We did have this answer during the broadcast. Is it 1 million, 10 million, 100 million, billions and billions? And I mean, even that, anyone who knows my Kahoots will know that I like to have answers be larger, shall we say, with most of the answers in. But it's really quite unfathomable. And Mike and I were talking about this before the broadcast. The answer is billions and billions, which most of you guys, this is like the highest percentage Kahoot ever. I should have gone harder. I was trying to be nice to you guys, and you just all killed it. So way to go. But yes, like there are billions and billions of galaxies, each of which have hundreds of millions of stars. I mean, it's really, I've heard it described that there's more stars in the universe than there are grains of sand on all the beaches of the world. And I mean, that no one can really conceive of that truly, but it's super, super cool. Any of those top 3, if you are those people, let us know who you are. We'd love to hear from you in the chat. Thanks for participating in the Kahoot, everyone. We are going to go to our 6 to 8s, Mr. Laveau's class. Anything you want to know about stars, universe? If you want to stump Mike, I always like it when the scientists get stumped. But we're going to head to North Palm Beach first. Welcome in, astronomy class. Hey! Okay. Mr. Laveau's students, I just want you to know, like every year we have Mr. Laveau on. His class is always like one of the most enthusiastic in the world. So you guys have a long tradition of excellence, and it's nice to see you guys. You guys rock. Okay.
We finished first and third.
Perfect. Way to go. You have a question for Mike?
Yeah, Larry, go ahead.
According to the conservation of energy, energy cannot be created or destroyed. So after a star dies, where does its energy go?
That's a great question. Yeah, so the question was, according to conservation of energy, energy cannot be created or destroyed. When a star dies, where does its energy go? Different stars die in different ways, but the general sequence is that the star will have kind of 2 parts. There will be the stuff that it sheds away, so the stuff that goes into the explosion or the nebula that the star makes, and there will be the stuff that's left behind. So that's the remnant, and the remnant can be one of 3 things. It can be a white dwarf, a neutron star, or a black hole. So the energy of that star is sort of divided between those 2 parts: the stuff that's shed away from the outer layers, and the remnant star that's left behind. Great question.
And on the note of the type of star, so our sun's going to be a white dwarf ultimately. We're not a neutron star. We're not a black hole. We're not big enough for that, which is a really cool type of thing in the universe in general. My face hurts from smiling. I'm going to let the kids ask all these questions. This is so much fun. Miss Albert's class, Madison Elementary, welcome in New York. Unmute your mic. Welcome to the broadcast. First one. This is so exciting. Come chat with me. I want to make sure.
Okay.
Hello.
So introduce yourself. My name is Brayden. What happens when a big star explodes but don't turn into black holes?
Yes. Perfect follow-up question.
So that's the question I didn't quite get. What happens when
a big star explodes but doesn't turn into a black hole? What happens to it? Which is a perfect follow-up to our white dwarf thing.
Oh yeah, great question. So not all stars have to form a black hole when they die. One of three things can happen. You can make a black hole, you can make a neutron star, or you can make a white dwarf. Now, massive stars are too massive to make a white dwarf, so they actually make a neutron star, which is an amazing object. These are the densest objects known to science. Far denser, many times denser than any sort of material on Earth or even in the sun. And these are incredibly dense objects, but they're just not quite dense enough to collapse into a black hole. So that's what you're going to get.
So, Mike, I'm just sending a quick message to one of our teachers. That's why I'm sorry I'm not back in right now. Oh, there we go. They just popped back in. Miss Buller's class, you got your devices back on. Perfect. A quick follow-up to this before you head to Georgia. With a neutron star, so when I think of neutron star, I think of the pulsating, looks like a lighthouse in space. Do all neutron stars do that? Or is that a unique subclass of them or anything else where it's like a pulsar?
So a pulsar is a neutron star that we know is giving off this pulsating signal, essentially that we're getting some sort of signal from. Not all neutron stars are detectable in this way because some have more rotation than others, some have stronger magnetic fields than others, and that determines how much radio emission they're actually giving off. Yeah. So not all neutron stars are strong enough emitting to be pulsars.
There you go. Thank you for that. I didn't know that. I want to note for our kids, and this might be, I actually have this in a story map that I'm going to share with all our classes at the end, on the Voyager record. So I think the coolest space mission of all time, the map that we sent out into the universe, like a cosmic message in a bottle, used pulsars in relation to the distance from the Earth as like a stellar map to guide any aliens to Earth if they were to ever come across the spacecraft millions of years in the future, which is one of the coolest things we've ever done as a species ever. And I'll make sure all our classes have that at the end too. So I'm so glad we're getting this star death question. This is fantastic, guys. Miss Bullis class, Catala, Georgia, welcome in, guys, and take us away. Hey. Hi.
All right. I wanted to know, do you know about what a quasi-star is?
A quasi-star.
A quasi-star. Yeah. So a quasi-star is essentially it's not a star because it's not fusing hydrogen, but these are these hypothetical, extremely massive objects that could have formed in the very early universe. So essentially, if you have something that's collapsing, but it's in fact much more massive than a star, so maybe 100,000 times the mass of the sun, you can make this massive object, which again cannot quite collapse to the density of a normal star, but is absolutely massive. And these are hypothetical; they haven't been detected, but they might actually be the seeds that eventually formed the black holes that live at the center of galaxies.
So two things about this. One, I forgot to say, Avery was second place in our Kahoot Miss Bullis class. So way to go, Avery. And two, I have done 1,500 broadcasts. That's the first time I've ever had a student ask a question where it's something that I hadn't even heard of ever. So way to go. And Mike, you knew that answer offhand. Cool, quasi-star. Great question, buddy. We're going to do another round. YouTubers, if you guys want to chime in with questions, we'd love to take some from you too. If you're shy, don't be shy. It's more fun when you're not. We're going to head back to our grade 6 through 8 astronomy group, Mr. Levog's class. Come on back in. Hey, guys.
Aylin has a question for Dr. Mike.
What made you want to learn about space, the stars, and the history of the universe?
Nice. What inspired you, Mike?
Yeah, that's a great question. Well, I actually, growing up here in Corner Brook, I never really cared that much about science, like all through high school even. Like I was okay at math, so I decided, okay, let's go study engineering, and maybe I can make some money off of being good at math, essentially. But actually, what really inspired me were a lot of the kind of great authors and popularizers of science that I only became exposed to kind of in my first few years of university. So, for example, I read books by Stephen Hawking and Carl Sagan and Richard Feynman, and all of these guys, they sort of were able to convey kind of the joy of figuring out how nature works based on a certain set of physical laws. And I thought that was just amazing. And I was also really bad at engineering, so I decided just, take the physics part of that and just do the physics, and the rest is history.
I'm so glad you mentioned this, because I think a lot of our students, certainly when I was growing up, I always assumed that if someone was in a career, like they wanted to do it from when they were 4. And like some of us are like that. I wanted to do this since I was 4 and talk about science and nature and excite people about it. But I'm so glad you mentioned that this is not something that came really, really young and came through popularization of science. Now, Carl Sagan is might be the best of all time. I'm going to make sure all our classes have links to Carl Sagan stuff. There's some YouTube videos that are spectacular with Carl Sagan quotes that hold up and are just as mesmerizing today as they were back in the 80s. But I really encourage our class, read these books. Science can be scary. I mean, you guys all have amazing teachers, which is great. You're keen, you're here. That's awesome. Some of you might hate science. And a lot of the top scientists that we have on this broadcast hate science or hated science when they were younger. Not in Mike's case, but like, can really just like it based on how it's taught. And sometimes it just takes a teacher, an educator that's going to reach you in a new way and inspire you with it. That makes such a world of difference. So thank you for that answer, Mike. That was great. Miss Albert's class, heading back to you. We're going to wrap up with Miss Bullock's after that. Time flies and you're having fun, but I will make sure all our classes have extra resources to keep the learning going when they're done. New York, yes, in.
Hello, I'm Pam, and I was wondering why is Pluto not a planet?
Why is Pluto not a planet? I love this. Mike, the Pluto question.
Great question. Yeah. So actually, there's a guy down the street from me. His name is Mike Brown, and he's the guy who killed Pluto. So he's told me about this at length. So Pluto is not considered a planet because essentially a bunch of astronomers got together and decided, okay, we need some definition for what is a planet, what isn't a planet. There are all these different objects floating around in the solar system, and they can't all be planets. Now, the definition they settled upon is that a planet has to be something that has cleared out its orbit. So as the planet goes around, it flings out other objects that are along the orbit. So there's essentially a gap in the number of objects that exist within that planet's orbit. So all of the actual planets have done this, but Pluto actually hasn't. So there are all of these other smaller objects that haven't been flung out of the sort of ring that Pluto orbits around. And for that reason, it essentially hasn't cleaned its room yet. So it's not grown up enough to be considered a planet.
So I want to follow up on this because I love this demonstration. Sometimes for kids, it's a little bit challenging. One thing that's funny too is like close to the sun, we've got our 4 planets. We've got Mercury, Venus, Earth, Mars. They're like little rocks. Then we got these 4 giant balls of gas. And then we got this little rock with Pluto. So it was always kind of weird. There's also some other things that are like Pluto that if we're going to include Pluto, Eris and Ceres jump to mind that like, okay, if Pluto's a planet, are they a planet? You should look these up. A lot of kids don't know about these, but they're super cool. Also, Pluto's super small. Our moon is bigger than Pluto. Like it's not that big. It's super cool. It's amazing. The astronomical community still loves Pluto. They just don't want to call it a planet. And I love that we cannot do a space program without getting this question. So Miss Albert's class, that was awesome. Thank you. Miss Bo's class, we're going to wrap up with one more query. Come on in and take us away.
What evidence do we have that the universe is still expanding?
Ooh, no pressure. Jeez, that's a big one. I like it.
Great question. So about 100 years ago now, a guy named by the name of Edwin Hubble, who actually worked where I work now in Pasadena, California, he observed galaxies, and he was able to figure out how these galaxies are moving. Are they moving away from us, or are they moving toward us? And what he worked out was that the vast majority of galaxies are moving away from us, and moreover, the farther away they are, the faster they are moving away. So what that tells us is that every galaxy is moving away from every other galaxy, essentially. So essentially, the universe is expanding, and we can directly measure the way that it is expanding from the motion of galaxies.
A way that I've always, I don't know who told it to me, but I really like it as an explanation for this for kids, because it's the Doppler shift is what we observe in this. If you've ever had an ambulance come towards you and its sound changes as it's coming towards you and then disappears and its sound gets deeper and deeper. So this happens with light as well as sound. So when we observe the universe, that's how we can tell that things are going away. It's more complicated science than you're going to run into in grade 5 through 8, but it's a fascinating process. And I'm so glad we got to throw in Edwin Hubble and his early work, because it's some of the most pioneering science of all time. Mike, we could talk all day. This has been so much fun, man. I'm going to encourage all our classes, starforge.space. Again, best project name of all time. If people want to check into your work more broadly, you've got a great website. This is on your last slide as well. All our classes, I'm going to get you this in an email in a minute, as well as a lot of other cool information like the NASA James Webb Telescope website, one of the best resources online ever, so you can check that out. But before we wrap up, I'm going to bring in all our classes in a minute to say a big thank you and farewell. Is there any final message you want to share with our classes about star formation, the universe, anything to inspire them and leave them with today?
Well, I just want to leave you with this, powerful idea, which is that the universe obeys physical laws everywhere. And that's the key thing that enables us to understand how the universe works. That we have these physical laws and we can apply them to anything that we can measure light in a telescope.
Mike, this is an amazing broadcast. I can't believe this is your first time joining us. You're an old pro. You're welcome back anytime, man. Mr. Laveau's class, Ms. Albert's class, Ms. Bullock's class, Florida, New York, Georgia, join us here in Newfoundland and saying a big thank you and farewell to Mike. Thank you so much, everyone. Have a wonderful day.